Now we're going to introduce the important idea of functions and how we write them. We will also remind ourselves of the basic trigonometric functions like the sine, the cosine, and the tangent. And of course, we will make a lot of use of these functions in our quantum mechanics. Now we're going to introduce the idea of functions and the use also of parentheses with functions. So, first of all, what is a function? A function is something that relates or maps one set of values, such as an input, which could be in our algebra a variable or sometimes called the argument of the function, to another set of values which we can think of as the output. So for example, here's a very simple function. The function f of x equals x plus a quarter. So that turns out to be a straight line. So on this graph here on the vertical axis, we're plotting f of x here is the value on the vertical axis against x on our horizontal axis. And we see it's a nice straight line. When x is equal to 0, for example, we find that f of x is a quarter. Now, as I just said, conventionally when we say f of x, we are reading this object here as being f of x. It's not f times x. And that's something we sort of have to deduce from the context here. F of x is not f times x in this notation, though that might not be obvious if you were merely thinking about what we said before about parentheses and multiplications and so on. And when we are writing functions like this, most commonly we only use these parentheses and not the other brackets. We might occasionally do that, but mostly we don't use the other ones. And hence it might be rather obvious from context there would be no point in putting these brackets or parentheses around this x if we were merely multiplying f times x. But that's not a terribly reliable notation, but sometimes it makes it more obvious what we're doing here, that we're talking about f of x and not f times x. Sometimes we will have more complicated expressions inside the parentheses. Now, that notation is used fairly rigorously of putting parentheses around the argument, but there are a few very commonly used functions, such as the trigonometric functions, which I'll introduce for you, in which we, for simplicity, just omit the parentheses when the argument is simple. So for example, the trigonometric function sine, instead of writing this out properly with sine with parentheses, we might just omit the parentheses and write sine theta. We should write it this way perhaps, it might be clearer, but commonly we also write it that way. Now I've also plotted out for us here the function sine theta. And that's a function we're going to use a lot, and I've plotted it as a function of angle along here. Note incidentally that if we go to minus some argument here, so here's sine of pi by 2 is 1, sine of minus pi by 2 is minus 1, and quite generally sine of minus theta is minus sine of theta. Similarly, for the cosine function, again, we might make this simplification of not bothering to write the parentheses here when we're saying cos theta, and we also don't typically say the of, cos of theta, but we might. Also, we will be using the cosine function a lot, and note it's very like the sine function, but it's sort of shifted sideways, so that cos of 0 is 1. And note also that this cosine function is the same for positive angles as it is for negative angles. So cos of minus theta is cos of theta. There's no minus sign in here. Now, of course, we know these sines and cosines and also the other related trigonometric function, the tangent, in terms of triangles. That's why they're called trigonometric functions. And here's a classic right-angled triangle. So this little symbol in here means, of course, we're talking about a right angle. And we imagine in this triangle we have a base and we have a height and there's an angle in the middle. So this base is also in trigonometry sometimes called the adjacent side because it's adjacent to the angle. That means beside the angle. And this side here is sometimes called the opposite side because it's opposite to the angle. The angle here is theta. And then the line between these two is called the hypotenuse. And often we will write these with x as being the length of the base, y as being the length of the height, or the magnitude of the height, and r as being the length of this third side of the triangle. So with those definitions, the sine of theta is y divided by r. Similarly, the cosine of theta is x divided by r. And one other trigonometric function, of course, is the tangent. Tangent of theta is y divided by x. Also, you can see that the tangent of theta is sine theta divided by cos theta. That would be y over r divided by x over r. The r's cancel, and therefore tan theta is sine theta over cos theta. And one thing you will have noticed here already is that I'm using the units of angles that are radians. And the radian is a more convenient unit of angle to use for any fundamental mathematical calculations. There are 2 pi radians in a circle, and 1 radian is 57.3 degrees. Remember, there are 360 degrees in a circle. So 2 pi radians in a circle, then 1 radian is 57.3 degrees approximately so. Now, there are another 3 versions of these trigonometric functions, and the notation here can be a little confusing. The cosecant is 1 over sine theta. So it would be r over y. It's sometimes written as cosec here. Alternatively, it may be written just as CSC, short for cosec. And the secant is 1 over the cosine of theta. So this is a confusing notation. The cosecant is 1 over sine, but the secant is 1 over cosine. So the secant would be r over x. And also the cotangent, sometimes written cotan here, or cot, C-O-T, is x over y, which is 1 over tan theta, which is cos theta over sine theta. Finally, another thing I should point out in this set of notations here is a somewhat confusing choice of notations when we're superscripting sine and cosine functions. Now, this particular function, called sine to the minus 1 of some number here, sine to the minus 1 of a, is also known as the arcsine. As I say, that's pronounced arcsine. And it's the function that works backwards to give us the angle from the sine value. So you'll notice it's really the sine function but laid on its side here. And as we go from minus 1, that corresponds to an angle of minus pi by 2. So sine of minus pi by 2 would be minus 1. And sine of pi by 2 would be 1. So it's really working backwards. And this notation here is one that is used in talking about functions. If we have a function f of x, then the function that maps us backwards from that value to the argument would be f to the minus 1 of x. And that's the way that this minus 1 is being used here. It's used to indicate an inverse function. So just to write that out properly, if we have a is equal to sine theta, the arcsine, or sometimes just written as a sine, or sine to the minus 1 of a would be theta. But to emphasize again, sine to the minus 1 of a here does not mean 1 over sine a. The superscript minus 1 here means the inverse function, not the reciprocal. This is the reciprocal. This is the inverse function. It's not the same thing. However, just to confuse the issue, when we want to write out the product sine theta times sine theta, which we could always rigorously write as sine squared theta, sine theta all squared here, we often use this notation where in this case the square, the 2 here, does mean that we are squaring the function. So this is not the same kind of notation as we had with the sine to the minus 1. So when we see sine squared theta, we understand that means sine theta times sine theta, not sine of sine theta, which would be corresponding more to the notation we had for the sine to the minus 1. Sine squared theta itself is a function that we will use quite a lot, and you'll notice that it's a positive function all the time, which it has to be, of course, being a square, and it's 0 at the origin and rises to 1 at minus pi by 2 and pi by 2. Similarly, cos squared theta, the same kind of notation. Cos squared theta means cos theta all squared. And this kind of way of using these squares in here is a notation that is almost exclusively only seen with these trigonometric functions and some of their very close relatives.